Let's go over an introduction to the fundamental concepts. The first question to ask yourself is, what is a time series? A time series is an ordered sequence of observations. And most of the time it's ordered according to time. Let's look at the examples in page 2 of chapter 1. You see four graphs. The first one is a graph of the daily average number of truck manufacturing defects. So on the y-axis you have how many defects, which seem to range from about 1 defect to 3.5 defects. And it's on a particular day, like day 1, day 2, day 3, and so on. The second example is one of yearly U.S. tobacco production, and that's pounds, millions of pounds of tobacco produced on the y-axis, and on the x-axis you have the year. So years start with, let's say, 1871, 1872, 1873, and so on and so forth. There's another graph that shows you quarterly U.S. beer production. So that's on the y-axis. That seems to range from about 30 million barrels to 45 million barrels, 35 million to 45 million barrels per quarter of beer produced. And then the quarters are shown on the x-axis. There's 4 quarters every year. And the fourth example is out of contaminated blowfly data, and that has the number of blowflies on the y-axis, and it's got days on the x-axis, like day 1, day 2, day 3, and so on. So those are 4 examples of time series, and they're ordered on the basis of time. And you can see from these examples different phenomena. Like the first series has fluctuation, but it's fluctuation around what looks to be a number close to 1.5. In the second example, you don't have fluctuation around a given number, you're going upwards. And not only are you going upward, but you can also see that in the early part, the fluctuation is smaller, and toward later on, the fluctuation becomes large. In the third example, you can see very much of an up down cyclical phenomenon. And in the fourth example, you can see that a certain observation is much, much bigger than the other ones. In other words, the time series you have contains an outlier. So how are we going to handle all those different phenomena? After this course, you will be able to handle these phenomena, and it will appear very simple. You'll be able to create models. The next example, which you see illustrated in the Lydia Pinkham data graph on page 4, here you have a matrix, not only one time series, but another time series. In other words, at each time point, you have a vector of observations. In this case, it's a 2-dimensional vector. But of course, we can generalize it to being a k-dimensional vector. We're just saying the letter k indicates how many dimensions. So this is a so-called vector time series, and you'll learn how to build a model that connects different time series. One of my classmates during this lecture asked the professor if it's tradition, or if it's the most common practice, to connect these sort of discrete observations, like connect the dots from day 1 to day 2, that sort of thing. And the professor answered that often they are connected, but it's an optional thing. You can just have dots, or you can have the lines connecting them. An outlier, normally you don't connect, but in that blowfly data we saw that it was connected. Most people do connect the dots in order to trace the pattern. It's a bit easier to understand. So remember, we said that a time series is an ordered sequence that's usually ordered according to time, but the fact is it doesn't always have to be ordered according to time. It can be ordered according to space. Let's say, for example, I set up a pollution monitoring station along a highway every 100 miles. So that is actually considered a time series, and we would call it a spatial time series. It's ordered according to space. But the technique in such a spatial time series is very similar to other time series analysis techniques because they're all ordered according to some order.